In this session, we will be talking about Arrhenius' definition of acid and bases. According to him, acid is any chemical that gives an H plus in aqueous solution. So when we say aqueous solution, means we putting a particular chemical in the water and it produces an H plus, also called an hydrogen ion. Now, there are main two types of acids. One of them called binary acids, which means it's got only two types of elements in there, and you have an oxyacids, which means they got an oxygen being involved in there. In case of binary acids, the most commonly used binary acids would be the one with the halogens. For example, I can talk about HF, that's hydrofluoric acid, talk about HCl, that's hydrochloric acid, HBr would be hydrobromic acid, and HI would be hydroiodic acid. And some other common, not so common rather, binary acids would be H2S, that's hydrosulfuric acid, or H3P, that's hydrophosphoric acid. However, the other more commonly names used for these H2S would be hydrogen sulfide or hydrogen phosphide for just H3P. But like I said, the binary acids with the halogens are more commonly used than with other elements. On the other hand, some of the most common oxyacids going to be H2SO4, that's going to be called sulfuric acid, H3PO4, that's going to be called phosphoric acid, HNO2, that's nitrous acid, and so on. So there are actually a lot of oxyacids, and if you have a hard time knowing the names for the oxyacids, I have another tutorial posted where I talked about how to name the binary acids and oxyacids. Oxyacids comes literally from the polyatomic anion, so we do have a lot of polyatomic anions, and that's why there are going to be a lot of oxyacids. Well, that's just a general idea of the acids and the common thing between both the binary acids and the oxyacids is obviously the presence of the hydrogen and a bunch of nonmetals in there. Well, in addition to just knowing the definition of the acid, it's very important to know 6 strong inorganic acids. All right, so out of those 6, 3 of them are binary. So I've got HCl being one of the strong acids, that's hydrochloric acid. HBr is another one, and then hydroiodic acid is another strong acid. And then you must know 3 other strong acids that are actually oxyacids. Okay, so first one of them being H2SO4, that's sulfuric acid, and then you have HNO3, that's nitric acid, and then HClO4, that's perchloric acid. So those are the total of 6 strong inorganic acids you see in the course of chemistry. And obviously there are other strong acids, but those are more or less organic acids. If you know these, that's usually good enough. Any other acid you see in an introductory chemistry course or even in a Gen Chem course is going to be a weaker acid. Okay, in addition to that, I do want to mention a couple of more things here. If you have only one hydrogen ion being produced by a given acid, it's going to be called a monoprotic acid. So make sure you know the difference between a monoprotic acid, a diprotic acid, and a triprotic acid. So an example of monoprotic would be HCl, HF, HNO3, and so on. So the common in all those monoprotic acids is the presence of only one hydrogen. In addition to that, you must know what a diprotic acid is. For a diprotic acid, you will have 2 protons in there. For example, H2SO4 has 2 hydrogen ion, or another name for those is the proton, obviously. And then you talk about carbonic acid, H2CO3, that's also diprotic, and so on. And then you also want to know triprotic acid. Triprotic means you have 3 hydrogens being produced in the given acid. And one common example for triprotic acid would be phosphoric acid, H3PO4. And I can probably write down another one, that's H3PO3, that's phosphorus acid. H3PO4 is phosphoric, H3PO3 is phosphorus acid. Okay, so that's all we have about the Arrhenius definition of acids. Let's talk about what a base is. Okay, according to Arrhenius, any chemical that gives a hydroxide, or another way of saying OH minus in aqueous solution, would be the base. Okay, so some of the common examples, obviously anything that has an OH in there, so NaOH or LiOH or BaOH2, those are all common Arrhenius bases we have in the list here. You also want to know some of the strong bases in this list, and I can, in a shorthand form, I can just write down MOH, where M is going to be any alkali metal. And where are the alkali metals? Well, alkali metals are going to be the first group metals, so I'm talking about lithium, sodium, potassium, rubidium, cesium, and francium. So for example, lithium hydroxide, sodium hydroxide, all the way to francium hydroxide, they're all considered to be strong bases. In addition to that, in the second group, or the alkaline earth metals, barium hydroxide is considered to be the strong base as well. In addition to that, sometimes some books may have calcium hydroxide and even strontium hydroxide to be listed as in a strong bases. However, they do have solubility issues in water. What that really means, you can dissolve only so much of calcium hydroxide and strontium hydroxide in water, but whatever amount of calcium hydroxide and strontium hydroxide has been dissolved in water will be existed in the form of a strong base, or we'll talk about what that really means in a bit. And other material, for example, any excess calcium hydroxide and strontium hydroxide may be precipitated out in the given amount of water. So they do have solubility issues, but the rest of these guys, the first group metal hydroxides and barium hydroxides, are obviously going to be the strong bases. I do want to mention one more thing here. Alkali metal hydroxide has only one OH in there. On the other hand, if you look at the second group metal hydroxides, you got two OH groups in there. So it's like, you don't really call them diprotic because it's not an acid, but you can kind of think of, okay, you do have two hydroxides coming from this material. Okay, so then you have, let's talk about strong acids and strong bases being strong electrolytes. And what does strong electrolyte really means? It means they ionize completely. So if I go ahead and write down HCl, because I remember it's a strong base, so when we dissolve that in water, it's actually going to break into H plus and Cl minus completely. Okay, so you're not going to have anything left behind in the form of HCl. Everything will be broken up into H plus and the Cl minus. That's what a strong electrolyte and completely ionized mean. That's one way of writing these reactions. Another way of writing this HCl reaction is with water. So you want to be familiar with both of those ways. For example, HCl reacted with liquid water, because that's what you're really putting that into. It actually makes H3O plus aqueous and Cl minus aqueous. Okay, so the take-home message here is sometimes you may written H plus, or sometimes you may see this written in the form of H3O plus. Both of those are actually the same. All right, some teachers prefer to write H plus, some teachers prefer to write H3O plus, and to be exact, H plus is usually written when you take in a Gen Chem course or an introductory course, but H3O plus, or also called the hydronium ion, is used mostly in organic. Like that's how you usually write that in organic chemistry, but that doesn't necessarily mean you don't see H plus being written in organic chemistry. So you want to make sure H plus, H3O plus is literally the same thing. Okay, let's write about maybe one of the bases. What if you have barium hydroxide, for example? Well, barium hydroxide being a strong base, we know it's going to ionize completely into water. So I have barium 2 plus aqueous. And since we said it's going to produce 2 hydroxide, so I'm going to make sure I write down 2 OH minus aqueous in there. So what that really means, if I have 1 molar of barium hydroxide in the beginning, you lose all of that and you make 1 molar barium 2 plus and 2 molar hydroxide in there, because remember it's a 1 to 2 mole ratio. If you lose 1 mole of barium hydroxide, you produce 2 moles of hydroxide in there. So that's what you're really going to be making. And when you're dealing with strong acids and strong bases, it's actually really easy to figure out the pHs and all that, and we'll talk about that in a little bit. I do want to write down maybe one more example before we call this off. So suppose I have H2SO4, that's another strong acid. And obviously, if I don't want to write that with the water, let's just write it like this. This can produce 2 hydrogen ions and SO4 2 minus. And obviously, when you're losing these hydrogen ions, it takes place one at a time. You lose the first one and then you lose the second one. Both of them will not be lost simultaneously. It's just one at a time. But however, you do lose 2 at the end of the day. And obviously, when it comes down to writing these weak acids, I want to go ahead and write down one of the examples for the weak acids. Suppose I have HF aqueous, and I'm writing that in with water, liquid. So when you're writing this within the form of a weak acid, which are not going to be in a strong electrolyte, they are going to be rather weak electrolytes, they ionize partially. So they do make H3O plus aqueous and F minus, but they do not break all the way into the product. So you can clearly see how you're going to be writing those in the form of an equilibrium expression, which literally means they have an equilibrium setup where you do have some of your reactants and you do have some of your products at a given time. On the other hand, when you're looking at these strong acids, which are strong electrolytes, they dissociates completely and you only have the products, you don't have any of the reactants left over. So that's the difference between those two. And we'll talk about these weak acids again when we talk about the Bronson-Lowry concepts of acid and bases. All right, if you have any questions about this video, feel free to leave any comments in the section below.